coming from UC Berkeley and has a new faculty position at Oregon. And she will talk about spectacular nucleosynthesis from early massive stars. After that, we'll hear from someone that comes not so far away, from MIT, Jingcheng Huang, who will tell us about unlocking clues to extraterrestrial life, a combined theoretical and experimental journey. And then we'll hear from Tania Barone from Swinburne University over there. And she will tell us about when does the initial mass function become bottom heavy. And finally, we'll hear from Cristhian Garcia-Quintero, an incoming postdoc to the CFA, who will tell us about large-scale cosmology, cross-correlations, and spectroscopic and imaging surveys. We'll start with Sanjana, please.
Hi, everyone. Thank you for joining me today. I wanted to take just a few minutes of your time to show you some work that I did with Alex G. at the University of Chicago on understanding the abundance pattern of a very strange star. And I'll show you exactly why it's strange. But the basic idea of this is that supernovae happen. They eject elements into the interstellar medium. At some point, a new star forms out of that material that's been polluted by the parent supernova. If the star is low mass enough, it lives for a very long time. And the atmosphere of the star will reflect the contribution of its parent supernova. So the atmosphere of the daughter star will contain clues as to the nature of the parent star and the parent supernova and the nucleosynthesis that happened. Okay, so the daughter star that we're interested in this case is this. Alex calls it the spectacular star because the name is otherwise not very informative. And what you're looking at here is the ratio of various elements with respect to iron on the y-axis, and then the element number on the x-axis. And the squares here are the measurements of these ratios for the spectacular star. The boxes are the typical values that you find in metalcore stars. This is a collection of 4,000 stars, and the typical values lie in those box and whisker regions. So immediately you can kind of see, even just by eye, that the abundance ratios in this spectacular star are huge outliers from the typical pattern that you would expect to see in a metalcore star. And so there's 4 features of interest. All 4 of them have been seen to some level of intensity in various stars before, but they have not been seen together and in such an extreme form until this star was observed. So the first thing is this huge odd-even effect. By that I mean if you look at something like sodium, and then you look at the even element magnesium, there's a huge change in the abundance when you go from sodium to magnesium. The odd-even effect is always present in supernova yields, but the magnitude of it being so large is what's of interest. And actually, this is what flagged the star as a strange star for us to begin with, because this signature is supposed to be the signature of a supernova that has been theorized but never been found or seen directly that we know of a parent stability supernova. So if in the early universe, really massive stars exploded through this mechanism called the parent stability, they are expected to produce this kind of huge odd-even pattern. So you see this pattern in this star. The other thing is that the lighter iron group elements, scandium, titanium, and vanadium, are very low compared to what is typically seen. The heavier iron group elements, nickel, copper, and zinc, are much higher than what's typically seen. And then finally, there's a tail of neutron capture elements, meaning from rubidium, from strontium, so on, onto silver here, there's significant amounts of these elements present, but then there's basically no barium. This is among the lowest measured values of barium ever. Okay? So there's these 4 different things going on, and we think that this is created, or most of the metals in this star were created in one very unusual event. This is not a trivial statement to make, because most of the time, when chemical evolution happens, lots of stars and supernovae contributes to making the next generation, the composition of the next generation of stars, especially because this star is at a relatively high metallicity, large amount of iron. So at this point, at a metallicity of minus 1.8 or so, you would expect the star to be heavily polluted by many, many supernovae. But we don't think this is the case. And I'm just using sodium to illustrate this here. The sodium in the star is on the y-axis, and the amount of iron, the metallicity of the star is on the x-axis. And the star is right here. And this is the general trend that stars follow as they undergo normal chemical evolution. So what we think has happened is some sort of star from this region made a lot of iron, but not a lot of sodium, and kicked the star off of the typical chemical evolution trajectory. So one event probably produced this signature. You can try to combine more and see if you get something interesting out of it, but we tried to basically produce the supernova pattern from, the pattern in the star from one supernova. Okay, so what can we learn about that supernova by looking at the abundances in the star? And so to do this, we started looking at things like which supernova can produce the metallicity of the star. But what event, how much energy and how much iron do you need to kick the star all the way over here in terms of its metallicity, for example? And this graph on the top shows you that criterion. Over here is the carbon to oxygen ratio in supernova yields typically. So what we're trying to do essentially is throw up all these little dots, are theory predictions. Throw up the entire range of theory predictions that we have available for supernovae, parent supernovae, hypernovae, and compare to the range of values that we see in the star, and to see if there's any tendency to favor a certain type of mass, for example, for the star that exploded originally. Or for a certain type of supernova, for example. And I think in the interest of time, I won't go on about this too much, but basically we looked at all of the key features. We looked at the metallicity, we looked at this carbon to oxygen ratio, which is a good tracer of the mass of the parent star. In case of a supernova, we looked at this odd-even pattern, the size of that odd-even pattern, whether you can produce this. We also looked at whether you can produce that tail of neutron capture elements, and one element as a proxy for that was zinc. After doing all this, there was no perfect match, but what we found was that the progenitor star, the parent star, should be more than 50 times the mass of the sun for at least the qualitative features that we see in the star's abundances to appear, to be matched. We also tried to produce a perfect best fits as best as we were able from theory predictions. And so again here, you're looking at the abundance pattern of the star in the red dots, and our theory fit is this zigzag line in blue. The best fit that we found two. One is an 80 solar mass star that exploded with 22 beta of explosion energy. A typical supernova is 1 beta. This is 22 into 10 to the 51 orders of explosion energy, very highly energetic explosion. There's basically no yields available for this kind of event that also include a jet that would have blown up the star, for example. Typically, these stars are not expected to explode. So if this star exploded, there must have been a jet or some kind of event, some kind of mechanism that helped it explode. And so we added up some patterns that we found that could correspond to the jets. Basically, it sort of works, but you know, the ion group of elements, that one pattern I was talking about, the heavier ion group elements being enhanced, that doesn't really work out in this case. We also added up this pair instability supernova pattern that I said it's a signature of pair instability supernovae. We added that up with again, some sort of neutron capture process pattern. But the trouble with this is that pair instability supernovae are not expected to produce any neutron capture elements typically. So even if this was a pair instability supernova, something must have happened during stellar evolution to create these elements before the star exploded, because they are typically not created during the explosion. So we found these fits, and they're promising avenues to explore. Bizarre pair instability supernovae, hypernovae with jets. We want theorists to calculate these yields and give them to us. And by theorists, I also mean me. We did find that, based on the signatures in the star, this low mass range, below 50 solar mass range, is not favored. This is interesting because stars above this mass are typically not expected to explode unless it's some sort of jetted explosion or a pair instability supernova, for example. So this pattern that is in the low mass star gives you one of the first observational constraints on nucleosynthesis in this particular high mass range. Okay. So this is an interesting discovery space. These events should be very rare, but in future spectroscopic surveys, we might find a few more stars that look like this, and it would be very interesting to explore. So that's it. Thank you for your attention.
So just to clarify, we don't expect such massive stars to explode, as you said, and therefore you're imagining making a black hole with, in the vicinity of which you channel matter into a jet, and somehow there is nucleosynthesis before this jet is produced close to the black hole. Is that the way you think?
So the way I'm thinking about it is more like maybe like a collapse star, where the star forms the black hole, but then there's still material. The jet forms, and then the star's envelope, maybe, or much of the outer material is ejected in an explosion. And then there's also nucleosynthesis in the jet itself, and the jet itself could have a weaker process.
But most of the material ends up in the black hole. It's just a fraction is channeled.
Yeah. Yeah, that's right.
Okay. Please, Rob.
Very interesting. I'm wondering how important you constrain about the total metallicity is, because that is essentially a non-constrained parameter. It depends on the environment where the progenitor star explodes, how the enrichment, the fallback time, the mixing goes about. And so these relatively high metallicities are not necessarily unexpected, right? If the thing explodes in a small halo, you have small fallback times, you can just enrich a small volume of pristine material.
Right, so if I understand you correctly, you're basically asking if we've thought about the fact that when the supernova happens, it pollutes a certain amount of material,
Yes.
and then you have a metallicity that comes out of
So my statement is the top line is essentially not a good constraint.
I see. So the metallicity here is the metallicity of the low mass star.
Yes.
And what we're saying is that the ISM that the low mass star formed out of must have had this sort of metallicity, right? And then if one of these stars explodes, we have relationships that give you the amount of iron and the explosion energy of the star. And so we have like a dilution, we have a sense of the dilution that would happen, and the maximum metallicity that you can generate as a result. So this is not just this is actually, the dots are actually the maximum metallicity you can possibly produce as a result of that explosion.
So the later statement I would question. Because it depends on the environment, it depends on the details of the mixing. And most of these calculations make relatively simplified assumptions that may or may not be correct.
Okay, so that will be very interesting to check more in terms of like galaxy simulations or something like that.
Exactly.
Talking to Kelly about this earlier.
Yeah, I mean,
Yeah.
you've been involved. And Alex is involved in some of these calculations as well.
Okay,
Okay,
yeah.
Morgan has another question about him.
So I'm curious, do we know for sure if this was a star that formed out of this enriched gas, or if it was like the companion to something that blew up and it's like enriched by that?
Right, so like
Moment?
the ejecta kind of
Yeah,
going on.
so like what
I
are its
think-
kinematics in the galaxy? Does that
So
offer
the
us anything?
kinematics, there's a section in the paper that talks about it in detail. I don't know very much, but there's no signs of a binary.
Yeah, so it's
that
not
it
going
was-
really fast, for example. Yeah, interesting.
Any other questions, comments? Yes, please.
I was wondering, the sodium versus iron plot, there were quite a few stars that also was similar outliers, right? So I was wondering,
yeah.
any of those showed similar residue?
That's a good question. I think the thing is, many of these that are outliers are only outliers in the sodium, but not in the other elements. And this is the only one that is an outlier in the nitrogen, sodium, potassium, scandium, all of them.
So if indeed it's a massive star, you would expect it to be extremely rare.
Yeah, so we do expect it to be very rare. And if it's the result of an over 50 solar mass explosion, we do expect it to be in this sort of metallicity regime as well, where the parent stability supernova descendants are expected to be found.
Let's thank Sanjana again.
Huh? Oh, yeah. Sorry, okay. So, hi everybody, my name is Jingcheng. I graduated from MIT Chemistry Department with a PhD back in 2022, and currently I'm a postdoc at MIT. Today I'm excited to share how I combine theoretical modeling with hands-on lab experiments to tackle questions in astrobiology. I believe many talks here are from theorists, modelers, and observers. So as an experimentalist, I hope to bring you a slightly different perspective and approach to this field. So today I'm going to briefly talk about three topics. So first, I'm going to show you how I use our photochemistry model to study ammonia as a potential biosignature gas. And then I'm going to discuss how my advisor and I use experiments to demonstrate life can thrive in a pure hydrogen environment. And then finally, I'm going to give you a very quick sneak peek into one of my current experimental projects. Sounds good? So in the first project, I study ammonia as a potential biosignature gas. For those not less familiar with this concept, so biosignature gas are simply gases produced by living organisms that accumulate in atmospheres, and when detected, can be attributed as signs of life on that planet. So to be a good or strong biosignature gas, that gas has to be detectable, has to be distinguishable, meaning that we can separate the signal from other gases, and ideally as few AVAC sources as possible to minimize false positives. So why am I interested in studying ammonia? Well, I'm interested in studying ammonia because it plays a significant role in biochemistry. So due to its high biousability, a lot of life, including plants and various microorganisms, can use ammonia, or can, should I say, absorb ammonia and use it as a nitrogen source. And additionally, ammonia stands out from all previously studied biosynthetic gases because of high water solubility, which makes atmospheric accumulation highly sensitive to the surface conditions. So I would say the most challenging part of this project is that a lot of researchers didn't realize how soluble ammonia is and how deeply it can affect the results. So many people just simply run their models without fully understanding the boundary conditions. And personally, I want to get it right by considering different surface conditions. So just to give you an idea how soluble ammonia is, I can see I plotted the log of Harris law constant, which measures solubility of a gas, versus different chemicals. For example, you can see gases like helium and hydrogen, they're not that soluble. For gases, for example, like CO2, which is SO2 or CO2, they're kind of soluble. And that dot over here is ammonia. As you can see, ammonia is 2 orders magnitude more soluble than other common atmospheric species. So since ammonia is so special, you might be wondering, have people studied ammonia before? And the answer is yes. For example, over a decade ago, our group studied ammonia for a very specific optimistic planetary scenario for a planet with a hydrogen-dominant atmosphere termed the cold harbor world. So the theory is, or hypothesis is, life on the planet may have evolved catalytic machinery to break the N2 triple bond and extract energy by fixing atmosphere H2 and N2 into ammonia. So here I want to reassess ammonia by considering different planetary scenarios rather than just H2 and different surface conditions, of course. So in this project, I use various models, but for today's presentation, I'll just focus on results from my photochemical modeling. Or more specifically, I use a photochemistry model developed by our group to simulate ammonia mixing ratio as a function of vertical altitude in exoplanet atmosphere, because our model is a 1D simplified model. So for this study, I consider a Earth-like or terrestrial exoplanet orbiting a N-dwarf star similar to GJ76. And I examined 3 different atmosphere scenarios, the hydrogen-dominated, N2-dominated, and CO2-dominated case. And in each scenario, I look at 2 different cases, so one with ammonia depositions and one without. And of course, in both cases, I assume that atmosphere ammonia is maintained through bioproduction. So for the case with ammonia depositions, so this represents conditions where there's active ammonia removal sinks at the surface, which means that there's ammonia dry depositions and ammonia wet depositions. Right now, everything is just on. Well, the case without ammonia depositions, similar conditions in which life produced so much ammonia to saturate the surface sinks. In that case, there's no ammonia surface depositions. In that case, there's no dry deposition, there's no rain out, and ammonia is only removed in the air by photochemistry. So what did we find? Well, in short, we found that ammonia can accumulate to a detectable level in the atmosphere with a more or less reasonable surface flux, but only if life is a net source of ammonia and produce enough ammonia to saturate the surface sinks. Or more specifically, when the surface is saturated with ammonia, the required bioproduction flux to reach detection limit is on the order of 10 to the 10 molecules per square centimeter per second, which is comparable to the bioproduction of methane on Earth, which is more or less reasonable. However, when the surface is unsaturated with ammonia, the additional surface sinks require life to produce ammonia flux at the levels around 10 to the 15 molecules per square centimeter per second. So this level is approximately 20,000 times greater than the current bioproduction flux of ammonia on Earth, and about 10,000 times greater than Earth methane bioproduction. So this flux is huge. And of course, for completeness, and also included N2 and CO2 dominated case here, even though currently for terrestrial exoplanets with high molecular atmospheres, the signal is just too weak to be detected by GWSD. So, in addition to using theoretical approaches, I've also employed lab experiments to investigate conditions that might support life beyond Earth. So in a collaborative lab project with my advisor, Professor Sarah Seeger, we explored the viability of life in a pure hydrogen environment. So why? Because many of the planets we've discovered have very puffy hydrogen-dominant atmospheres, and quite a few astronomers, at least back then, believed that pure hydrogen somehow is not compatible with life, and that life cannot survive there. So with this project, we want to show that life, in this case, we use 2 single-celled microorganisms, E. coli and yeast, can survive in a 100% pure hydrogen environment, and therefore we want to challenge the preconception that such an environment will somehow be detrimental to life, and ultimately by showing that life can adapt and survive in an environment that's vastly different from the natural habitats, we hope to expand the scope of the potentially habitable exoplanets. So on the left, you can see a simplified schematic of our procedure. The concept of this project is very straightforward. We basically took a bottle and add a small amount of nutrient liquid at the bottom, seal it, sterilize the whole bottle, and then flush the headspace with the gas we want to test. So in addition to H2, we also tested helium, pure helium, CO2 N2 combo, and air control just for completeness and for comparison. After setup, we just place the bottle in a shaking incubator, like that, and you see if the microbe will grow. So on the right, you can see are the 2 photos I took. On the top, you can see the bottles with the different gas line. I took the photo during the flushing phase. And at the bottom, the bottles are in the shaken incubator. Okay. So by the way, the device attached to the side are oxygen sensors made by one of our former postdocs to ensure the environment inside will remain anoxic, which means the oxygen-free throughout the whole process. And some of you might be wondering, what's with the QR code pattern at the bottom? Well, we mounted the camera outside the shaken incubator to monitor the experiment, and the patterns are there for us to stabilize the image. So what do the results look like? So on the left, you can see a photo I took just after one set of experiments. Here you can see 2 bottles. One is the control bottle with just no microbe inside, just the blank. The other with microbe inside. I believe that's E. coli, I think. And notice how one liquid is clear, the others look like milky, melted, buttery. So just by visually, that's indication of microbial growth inside. And quantitatively, on the right, you can see 2 growth plots. For example, just one for E. coli, and that's for E. coli, and this is for yeast. And for both plots, the y-axis represents microbial growth, and the x-axis shows time in hours. And the different colors indicate different gas environment. For instance, the black curve represents the air control, and the red curve for both plots represent hydrogen case. And as you can see, both E. coli and yeast, they grow. They grow in a pure 100% hydrogen environment. In fact, if you look closely, they also grow in a pure helium and CO2 N2 as well. And for the final part of my talk, just give you a quick sneak peek into one of my current experimental projects. So right now, most of my work is focused on one planet, specifically Venus. Why? Because back in 2021, Professor Gree from UK and my advisor led a research team published a paper in Nature Astronomy claiming detection of a gas called phosphine in the Venusian cloud. I know the results still somewhat controversial. I'm not here to show to you guys it is there or it is not there. I'm simply here to say that that finding sparked our interest, my interest, to study Venus further. So what I'm trying to do right now is designing my own modernized Miller-Urey type experiment to study abiotic synthesis of biomolecules in the Venusian cloud. I put the figure there just to remind you what the original Miller-Urey experiment looked like. The original Miller-Urey experiment was performed by 2 great scientists, Stanley Miller and Professor Urey, back in 1952, to study abiotic synthesis of biomolecules in ancient Earth atmospheres. So, as I mentioned, my goal here is to study the feasibility of abiotic synthesis of biomolecules, so small molecules like building block, amino acid, nucleobases, in situ in the Venusian cloud. I'm going to give you a quick sneak peek into one of my experiment setup, and here it is. I took this photo over the summer while building my setup. In fact, I started this project literally from the ground up, to be honest. When I started, I didn't even have a fume hood. So everything you see here is either designed or acquired by me. In the photo, you can see the glass manifold behind me that looks different from the original one. You can see the reaction flask, as I call it, the Venus in a bottle. And attached to this glass manifold, you can see a vacuum gauge here, you cannot really see, a cold trap and a pump, allowing me to introduce the exact amount of gas into the reaction chamber. And I'm happy to report that this experiment is actually running as we speak. And here's a very short video of what it looks like in action. And you can see the lightning spark inside, and the liquid down there, instead of water, I use concentrated sulfuric acid. And for the test bait, instead of ammonia and methane, I use 90% CO2 and 10% N2 just to mimic Venusian conditions. So I know I don't have time to cover all the details, so here's my contact information. I'm also going to stay around a bit longer just in case you want to talk. You can scan the first two QR codes if you want to read the paper directly. The first one for the ammonia work, the second is for the life in hydrogen. You can also scan the last one if you want to know other projects to work on and contribute to. So I'll open the floor to questions. Of course, thank you so much for listening.
For life in an atmosphere made of hydrogen or helium,
Yes.
I assume that the microbes were not, I mean, they have their own nutrients
Yep.
that do not come from the atmosphere. So why should it be surprising? They don't care. I mean, the atmosphere is inert in
Yep.
some sense. So whatever inert gas you put in the atmosphere, they don't care about it as long as the pressure is reasonable to allow them the chemistry.
Yeah, so that's a very good point. That's actually the point of the whole project, to show that the gas doesn't kill the microbes. Because a lot of astronomers, at least back then we talked to, they say, oh, pure hydrogen, life gonna die there very quickly. We just show that with nutrient, microbes can grow there. That's the whole point. And hydrogen, pure hydrogen doesn't kill life.
Well, it will kill us, right?
Yes, of course. Yes. So yeah, that's a very good point. As long as there's nutrient inside us, the broth we call it, those little guys will grow. Will grow inside.
Right.
Very interesting. I have a question that I guess reflects my lack of knowledge of this field. So I always thought hydrogen atmospheres are associated with giant gas planets, which vice versa implies there is no liquid surface around. So how do you fit these two things together? A surface, a liquid, as Ari pointed out, and hydrogen, a pure hydrogen atmosphere.
That's a very good point. Yes, a lot of gas planets, gas giants have pure hydrogen environment. For that project, we just say a lot of, in the future, in the near future, a lot of the terrestrial planets we discovered, because hydrogen have a very, puffy, right? So it's likely that we're going to discover more hydrogen-dominated terrestrial planet than, so we just want to study, can life just survive there?
Would hydrogen easily outgas and you remain
It
with
depends on the
organic
surface
liquid?
gravity and the temperature, the surface temperature. There is Jeans evaporation, of course, but yeah,
Occurs.
you can imagine situations where you have liquid water with the hydrogen atmosphere, in principle. Any other comments? If not, let's thank Jingcheng again.
Great. Hi all, I'm Tania. I'm a postdoc at Swinburne University in Melbourne, Australia. So whenever I see someone have a specific question in a talk, I always expect a coherent answer at the end. So maybe I was a little ambitious with this because I've got some preliminary results, so I'll give you a bit of a taster for what we're finding, but I don't have a concise answer just yet. But hopefully by the end of the project we will.
Do you have a microphone? Oh. Yeah.
There's a microphone here, and I think it's on.
Yeah. Thank you.
Can you hear me a little bit
Yeah,
better now?
much better.
Perfect. So before I dive into the science project, I'll just give a little overview of the data that's enabling the science. So I'm part of a survey group called the AGILE survey, Astro 3D Galaxy Evolution with Lenses. So this is a survey of strong gravitational lenses. So I'm here visiting for a couple of weeks to work with VTran, who's also part of the survey. So strong gravitational lenses enable a huge variety of science. On the high redshift magnified sources, the mass distribution of the deflectors, cosmology. So they're really valuable targets. The problem is that they're also quite rare. So that's the purpose of this survey, is building up a sample of these valuable targets. So we started with a few thousand candidates that were identified by convolutional neural networks in wide area surveys, imaging surveys, and then we've been spectroscopically following them up. So we currently have followed up about 130 systems to measure the redshift of the deflector and the source. And as part of the program as well, we've been collecting lots of wonderful HST data. So we've had a SNAP and a GAP program. So the GAP program's still ongoing. So that's where a lot of all these images come from. So the one in the top left, that's our survey symbol, the smiley face lens. This one here is also really nice because you've got the main arc and then the another sort of deflection around that little group member there. So we've got a huge range of targets. So the first catalogue V published a couple of years ago, and the second one is in the works. So if galaxy evolution is your field, if strong lenses are useful for your science, have a look at what we've got. Because as I mentioned, they do enable a really broad variety of projects. So again, if that's of interest to you, you can have a look at the website. Here we go. So this is, although I'm still in the works to submit the paper, I've already put all the data on our website, so it's all already public, so you can have a look at the targets we've got and all of their redshifts. So this is just a bit of a scroll down, so you can see there's quite a range of deflector types, so galaxy scale, groups, clusters, red dusty spiral arcs, high redshift star-forming galaxies, targets with 2 arcs, like that one there. So a huge variety of stuff. But the reason why I'm sort of interested in this sample is to answer specific galaxy evolution questions. And the one I'm looking at now is how we can study the low mass end of the initial mass function, in particular redshift 1. So I'm using these 2 lovely targets, so lensed quiescent galaxies. So I know there's quite a broad range of research fields in the audience. So I'll just very briefly go over what I'm talking about. So when I talk about the initial mass function, I'm talking about when you have a molecular cloud collapse to form stars, what is the distribution of stars that will form? So we know that in general you have very few high mass stars and a whole bunch of low mass stars. So in particular, the low mass end, so anything less than about 0.4 times the mass of our sun, they make up the majority of the stellar mass in a galaxy. Yet they contribute only 1% of the light. And so this low mass end of the initial mass function is really difficult to constrain for that reason, because we're looking for 1% variation, 1% changes in the spectra. And any any recent star formation, any of these massive stars just completely outshine that majority population. So it really is difficult, but it's incredibly important because, as I mentioned, they make up the majority of the mass. And so when you measure a stellar mass of a galaxy, when you measure its age or these other galaxy properties, they all hinge on this assumption. And for the most part, people just kind of pick their favorite distribution. There's because it's really difficult to constrain it. And this would all be fine if it were the same everywhere, if it were universal. We would just measure it for one molecular cloud in the Milky Way and then be done with it. But the problem is that this distribution has been shown to change not only between galaxies, but also within a galaxy as well. So in the center compared to the outskirts. And if it changes within a galaxy, is that perhaps due to a redshift dependence? Could it be due to a metallicity dependence? There's all of these possibilities. So understanding how this varies is currently not very well understood. And again, part of that comes down to the fact that you need such high signal-to-noise spectra. So I know, people studying stars, they get 100 signal-to-noise spectra all the time, but that's not very common for galaxies, especially not in a survey of galaxies. And so this type of analysis at the moment is really constrained to low redshift, so really close by massive quiescent galaxies. Because you also need very high sensitivity in the near infrared. But thankfully, with the combination of JWST's near-infrared sensitivity and the additional boost that we get from lensing, so if these galaxies are magnified, I think 5 or so times, we can finally get that really high signal-to-noise spectroscopy that we need to disentangle the low mass end of that initial mass function. So that's what we're doing here. So this data is very new. It just came in a couple of months ago. So I've been having fun with the JWST pipeline. So that yellow box, that shows the near-spec IFU. So we're just probing the brightest parts of each of those arcs and integrating it to get a single integrated spectrum. So it doesn't really matter if you can't read from where you are the labels, but this is really just to show the yellow lines, that's showing IMF-sensitive features. So features that we know will vary depending on that low mass end. And then these orange lines are other stellar features in that part of the spectrum. So it's really detailed. And why did we pick these two targets? Well, firstly, because there wasn't much choice, because, again, these targets are rare. In particular, lens quiescent galaxies are very rare. But these two targets were a perfect pair for this study because based on what we know from low redshift, we predict that they will have different IMFs. So from low redshift, we know that galaxies with higher velocity dispersion, so that tend to be bigger, more dispersion dominated, they tend to have more of these low mass stars, an overabundance of these low mass stars. So these two galaxies, these two length galaxies, they have a similar mass, same redshift-ish, but very different velocity dispersions. And so if what we know holds from low redshift, we should expect that one will have more of these low mass stars than the other. So that's what I'm looking for here. So here I'm just showing the specific IMF sensitive features and comparing one spectrum, one galaxy to the other. So one is the dashed line, the other is the dotted line. So in some of the features, they're very similar, but we're seeing, so for example, sodium-1, they're very similar. But magnesium-1, titanium, this wing forward band, the iron hydride, we're already seeing significant differences. So this is, as I said, a bit of a taster, quite preliminary, very new. So I don't have an answer for when the IMF, which one will specifically be more bottom heavy, but it's exciting that we do see variations already in these features. So hopefully, within a few more months, we'll know which one's which and have a more clear picture. So just to quickly summarize, so gravitational lenses enable a huge range of science, and that's why I really like working with this data set, because I've jumped from science case to science case over the past year or so. So I've just really talked about the stellar initial mass function at redshift 1, but some of the other work that I've recently been doing is also using lenses to probe the circumgalactic medium. So these are bright background sources. You can look for absorption features at the redshift of your foreground deflector. So that's something that I've been really interested in. And also using these targets to do cosmology. So this lens in particular is a great candidate to study cosmology with, because you've got so many arcs at a range of redshifts. So if you're also interested in any of those other topics, I'm happy to talk about that as well. But if not, I'll leave it there. Thank you.
Tania, with respect to the IMF, the initial mass function, at low masses, there are two parameters. One would be the slope and the other one the cutoff, because obviously the Jeans mass or the the minimum mass of stars could depend on metallicity. So can you constrain both or just combination?
So I'm hoping to be able to constrain both. So at the moment I'm doing sort of the very simple models where you've just got a single power law, looking at those. But I'm hoping that because our data is just so high signal to noise, I will be able to also constrain like the low mass cutoff and also be able to look at double power law models as well. But at the moment I'm just starting simple and hopefully I'll graduate in complexity of the model soon.
Yes, please go ahead.
So, is it possible to, so these features that you're talking about that are sensitive to the initial mass function, is it possible to distinguish effects of microlensing within those individual images? If you had like individual areas that were microlensed because of the foreground galaxy, would that cause differences in the spectra?
So in the spectra that we have, while we're using the NearSpecs IFU, in order to get to the signal to noise that we need, I'm just integrating across the whole IFU. And so I think any very minor effects like that will be sort of washed out when I combine them. And this also with, I didn't show here, but I've also got some like kinematic maps looking at like the individual spectra. So the individual spectra aren't probably quite high enough signal to noise to see any additional effects like that.
There is also the time dependence, right? So microlensing will be, if you average over time, it will go away.
Yes, true. And this was, there are only 4 or 5 hour exposures. So yeah, I wouldn't expect to see that in this data.
Okay, please.
So you mentioned the massive star, how shines the lowest star, right? So I wondered, would result SED fitting or non-parametric star formation history assumption will help you to understand the initial mass function if you have the photometry data with ZWST? So
yeah, that's an interesting point. Even with your photometry, all your photometry is still going to be dominated by the brightest light. So ideally, yes, you can get your multi-bands over a really wide wavelength range in order to try to constrain the population of stars. So that will get you, I guess the problem is that then what you're measuring is also, you're also measuring the star formation history, and so that's not easy to disentangle from this initial mass function, because this is just really, really small variations. And so something like an SED fit's not going to be able to capture that incredible sensitivity. And so for SED fitting, you will generally have to assume your initial mass function and leave it there.
Gary?
Yeah, maybe you mentioned this and I just missed it, but are you also looking at the metallicity of these objects? Because it's the metals that cool the gas as it collapses to form the stars. And so you might expect there to be a difference based on the abundance of these metals.
Yeah, good point. So no, I didn't mention it. Thankfully, we also have extensive ground-based rest frame optical data for these two targets, and so we've been able to constrain the metallicity from rest frame optical absorption features as well. And so we have the magnesium abundance, which also indicates that they should have different initial mass functions, because again, the magnesium abundance tends to correlate with IMF. So that is something that we're able to test, thankfully.
Okay, let's thank Tania.
No, I hope you can hear me. I guess you can hear me, right? So I was the lucky one to go last, but I hope I will make you sleep a lot. So my name is Cristhian. I am a new postdoc, so I just started here on September actually. So I'm here with an NASA Einstein Fellowship. And then I was even in Mexico when I got this email about, okay, you would like to present, and I said, okay. But then it was a bit awkward because then I have two problems. So one of them it was that some of my projects are in a preliminary stage, and some others I cannot tell much because the DESI data is not public. So then I thought I could present this science case that we are also working with some other group of people in DESI. So it's related to cross correlations. So let me tell you a little bit this story about this. I have the impression, to be honest, that right now we're living in a very nice time regarding cosmology because we are living the transition between the stage 3 and stage 4 surveys. I remember like around 6 years ago when I was back in Dallas, I was still using DS01 and actually the DESI and LSST seem very far away. Right now, LSST is knocking the door and DESI is already here providing with data. So this is basically I highlighted DESI there because I also do work with these instruments. So most of my research gets consumed by DESI, which, yes, very nice. Thank you so much, Abhi. So basically, stage 4, if you ask around to people, they will tell you, okay, it is a better instrument, more precise. I don't have a plot here, but there is also a plot with the number of redshift you can measure when you use DESI compared to the precursory survey, which was the SDSS mission. And then you can see that, for example, with SDSS, we measure around, well, they measure around 2 million galaxy redshifts, and with DESI, you expect to measure 40 million galaxy redshifts. If you go to documents, you will see that the stage 4 survey basically allows you to constrain better you get a higher figure of merit for dark energy equation of state. So that will be the formal definition. But if someone in the street asks you, you say it's more precise. So with DESI, as you know, I'll just go quick here because of the time, we were able to measure baryon acoustic oscillations, which actually is this signal that left an imprint in the galaxy clustering history of the universe, when that comes all the way from the decoupling in the sound wave oscillations in the primordial plasma. Once the decoupling happens, this freezes, and then you can measure it right now as an excess at a given scale that you can project in redshift, so you can get measurements for different tracers. And we got some results on dynamic dark energy, and you will hear more about it, I'm pretty sure, next year. However, what I want to talk about is that if you have instruments like DESI that are, I mean, you're spending money on these instruments, right? Of course, we don't spend as much of the particle physics experiments, but ideally you want to get every drop of information as possible. So then you can notice in this chart here that you have some experiments like Euclid and LSST that are going to happen and take data, but you also can notice that we have other precursory surveys that are not like DESI. DESI is a spectroscopic instrument, so it's very good at measuring the redshift and tell you the angular position in the sky. These other surveys are imaging, so they are not very good at measuring the redshift. They can tell you within some probability, but you can get the shapes of the galaxies. So the science case I want to talk to you about, because typically when people talk about DESI, they only hear BAO and full shape and RSD analysis, is that if you look at the DESI footprint, you can, and this is a flow chart, this is a graph where you can see the different DESI observations, but you can also notice that these other surveys that I told you about that are imaging, they work with photometry, they also have observations that can overlap the DESI footprint in some areas of the sky. So here I'm showing you HSC, KIDS, and DS. So in particular, is DS the one that has the biggest overlap with DESI. So you can notice it here in some areas. And I will say that it's not a coincidence, to the best of my knowledge, that most of the DESI observations, they start to happen in these regions where you have some overlap, because it was requested like this by the team, so you don't have to wait till the full DESI data to do this cross correlations. So basically what we want to do is to use the galaxy redshifts from DESI and do cross correlation with that. But also we can use the shapes of the galaxies, do cross correlations with them, given the large scale structure. And in the areas where you have some overlap in the footprint, you can cross correlate what we call lenses and sources. So in a very conceptual way, you're cross-correlating positions, galaxy positions and shapes, and shapes and shapes. So this is something that is going to happen. You will see the real data about these constraints in around March next year. But what we have been doing so far is that we have been preparing our pipeline to this analysis. So I will just tell you very quickly that we have made, this whole team, I work more on the modeling side, but we have simulations that we have built in order to try to match what we will expect from these surveys. So basically, we have these buzzer simulations that are Lycon, and we can tune those simulations given the redshift distributions of DESI and the redshift distributions of these other surveys. And one of the tricks here is like we divide the quadrant of those simulations into different hill pikes regions so that you can match the expected overlap in the footprint that I was showing you in the previous image. And this is very good for covariance testings, but we can then combine these different hill peaks regions to get a representative region that we will use for each of these different correlations. So in the case of the S, you can see here that these around 900 square degrees are represented by this region, but we will use these other regions for clustering and lensing. So once you have the simulations, you can do measurements, and you can see here that if I compute the same correlation function, this is the cosmic shear signal, you can get actually match very good what the measurements you are extracting from the simulation. However, for realistic simulations, you need to introduce noise, for example, shape noise, or I remember Claire was talking last week about intrinsic alignments. You can try to put those ingredients into the simulations and do the measurements again. And then the stage that we are in right now is that we are fitting our pipeline that we'll use for the real data under these simulations. And here I'm showing you a plot for the constraints on cosmic shear. This is on the horizontal line. Basically, you have omega matter, and here you have a state which is a combination between sigma 8 and omega m that is typically used by the weak lensing surveys community because they can constrain better that parameter. So you can see here that the blue plot is the constraints that I will get if I feed a fiducial data vector, and then the red plot are the constraints that I will get if I feed the measurements of cosmic shear from our simulations. You can see here that I have some stars. These are basically telling you the best fit of the fiducial data vector and the best fit of the mock mean. And we have 8 simulations for these fits. We can also go ahead and fit the whole set of 3 times 2-point correlation functions. And you can see that you still can recover the fiducial cosmology within 1 sigma, but then you start having some projection effects, because typically what happens in this weak lensing analysis is that you model a lot of stuff with noise and parameters. And I remember Alex Amon was talking about this like around 2 weeks ago. So then that can lead you to projection effects and making the contours a little bit bigger. So right now what we have in DESI is that we have, in a parallel analysis to what people is doing in BAO and full shape, we have survey simulations that allows us to tune our pipelines for these cross correlations. We have our own binning scheme. These bins that you see here are different from the ones that are published in the DESI BAO analysis because we care about the redshift evolution of other observables instead of what people do in BAO care about. We also have our own blinding scheme. If you go to the DESI paper, you will about BAO, you will see that the blinding happens at the level of imprinting a shift in the redshift of every galaxy. It happens at the catalog level. In our case, we do it directly at the data vector level, which means at the level of the correlations, because it works, and if you apply the same blinding that BAO people do, it doesn't produce a shift. We have pipelines to measure the galaxy-galaxy lensing correlation, and we have a pipeline to do cosmological analysis. Right now, we are in a pre-blinding stage. We're very close to do that. But you can see here what we will expect to have at the top of the cosmic shear once we add the galaxy clustering by Deci and the cross correlations, so you can see here the complementarity. I know I have a lot of stuff here, so I will just jump in. But I will say that another thing I am particularly interested, I'll just go very quick on this, is that with this data, we'll also be able to test modified gravity. So we have parameters that are sensitive to the growth rate of a structure, and we have parameters that affect the Weyl potential that goes into the deflection angle in weak lensing. So in the same way that BAO is telling us about dynamical dark energy, we can also will be able to test modifications to gravity at very large scales. And in the future, and then I finish with this, Avi, is that in the future with more observations and passes in Deci, this overlap is going to become better. We also are aware that there are other surveys that have more overlap. But even in the future, things like LSST are going to give us a footprint overlap of around 5,000 square degrees. And this is a way also of promoting synergies between the surveys. And that's all I will just stop like this. Thank you.
Attention with respect to dark energy or not yet?
Yeah. I mean, I know Daniel is there, but in my case, when I saw that, I was a bit afraid about the LRT sample. But I'm typically more cautious on that regard compared to other people in the collaboration. I will say that it might happen, but we'll just have to wait for the data to make sure. And also try to keep digging into these particular tracers. I will just say that the time will tell you. But typically, also, I am very bad with these predictions, I would say, because when I was an undergrad, I remember people was talking to me and I was saying, no, we are not going to detect gravitational waves, it's very hard, and then you got detection the next month. For dark energy, I was thinking, you know what, I think it's lambda somehow, I should work on modified gravity. And then Deci found this thing, so then it's like, typically I get it the other way.
Maybe you should try always the opposite.
That's what I mean, who knows?
Okay, any comments, questions? Looks like everything was clear. Thank you so much.
Thank you.